All right, welcome back, everybody. So we are going to continue off today where we left off last class. Before we just get started on that, I just wanted to talk a little bit about the email that I sent out yesterday. So that email should have made clear all of kind of the updated elements of the course, I guess I would say, how things have changed a little bit, maybe from what we had said in our first class. The first thing I wanted to talk about was the marking scheme, in case that wasn't clear in the email. So basically what I did is I took three components of the course, which were the two assignments and the final exam, and I added 5% weight to each one of those. And it works out now that if you add up all of the parts of the course, it adds up to 120. So what I'm going to do is just at the end of the semester, look at which component of the course you did worst in and take 20 points off of it. So if that happens to be one of the assignments are already worth 20, so they just get written off. They just disappear. If that's your exam is worth 30 at the moment. If we take 20 off the exam, that brings your exam value down to 10%. So what this really does is it gives you a lot of flexibility in terms of how you want to play things out for the rest of the semester. If you just want to like not do assignment 1 or assignment 2, you have that choice. That just means the remaining parts of the course will be 100% of your grade. But if you do everything and you keep up with the unit assignments and you do everything kind of on track, what that means is your final exam would then only be worth 10%. So if you're the kind of person that likes low stress exam periods and would rather focus your energy during that time towards your other courses, maybe that's the solution for you. Or if it was me, what I'd probably do is just do my best on every part of it, and then you kind of have this insurance, right? If some part doesn't go as well as you'd hoped or whatever, well, we throw it out and base your grade on everything else. So this is sort of my way of giving you flexibility, because you can decide what you want to do and not want to do going forward, but also, I guess, for those that have been keeping up and don't want to have a reduced number of assessments, because that means your grade is made up based on fewer things. Some people see that as a higher risk situation. It kind of takes care of that issue as well. The first assignment, which was, that was posted a long time ago before the strike, the due date for that is this Thursday. And I've been having a few questions trickle in about that, so please don't forget about that deadline. My usual policy in this course is to dock 20% of the grade's value every day you're late. So what that means is if it's more than 5 days late, it goes down to 0, which means you can still do it, but it won't form part of your grade then at that point. That becomes your automatic 20% that disappears at the beginning. Just a note, I think I sent this last night, the unit assignment for the previous unit is due today. In fact, I think it might be set for what time? Did it already pass? Maybe it did. Maybe it passed at 1, I forget. The next one that we are going to finish today, I expect to finish today, is this one on ozone and CFCs and UV light, this sort of stuff. I expect this is going to be due next Tuesday. And then we have a final unit, which I expect to be done Thursday, actually, on air pollution, which is going to be on climate change. And that'll probably be due next Thursday. But, if you're doing it with me, if you do it along with the course, you shouldn't have to worry about those due dates at all. You should just do them, click them, and we're good. Anyway, the unit assignment should be up. Slides are up for the next unit as well. And we might get to that today. The second assignment is the video assignment. And I have the due date for this as April 7th, which means you guys have a good couple of weeks. What's today, the 14th, 15th? So that's roughly 3 weeks. This assignment can be done in groups. In fact, I encourage to do it in groups if you can, where it means producing a video that is somehow chemistry related And you know, it's obviously chemistry related, but it also teaches or communicates a concept in chemistry or science more broadly. And if you read the description of the assignment, I urge you to read it very closely. If for whatever reason a video assignment is not something you can do or feel comfortable doing, I'm open to alternative proposals. Okay, so I'll leave it at that. I'm not going to just give you carte blanche to do whatever you want. Make me a pitch if you want to do something different, and we can discuss what that might look like. There's a whole bunch of stuff in the assignment description too about how you can submit your assignments to me and stuff like that. But for now, start thinking about ideas. You got a couple of weeks, and it'll be due close to the end of the course. All right. And that kind of wraps things kind of up for us. The only other thing left we have is the final exam. And the final exam, what I said in the email and what I'm going to do is just make the exam period anytime you want within the first week of the exam schedule. So what that means is the exam becomes available online, and you can choose whatever time you wish to start. Once you start, though, the timer starts, and you'll have probably 3 hours. It almost never takes people 3 hours. It was interesting, like I did it on Acorn last year, and I get stats about how long people take. I think only like 3 people out of 380 last year took longer than, say, an hour and a half. But you have 3 hours. Take the time if you want it. So this way you can, again, it's flexibility. You can squeeze it in anywhere you want into your schedule. And it's going to be cumulative based on everything we've done so far this year. I would recommend you look at the old unit assignments for examples of the sorts of questions you're going to get. And it's going to be mostly factual, kind of based stuff like that. Cool. So what that brings us to at the moment is our next unit, which is, well, not our next unit, our current unit. And our current unit is continuing our discussion of ozone. And we spent a lot of time talking about tropospheric ozone, how that's bad, breathe it in, can hurt your lungs. Then we talked about the ozone layer, and the ozone layer is up in the stratosphere. This is beneficial to us because it filters out the most harmful wavelengths of UV radiation coming from the sun, and it helps, protect our skin, and it, prevents us from developing cancer and things like that. It's not perfect. It doesn't take all the UV light away, and there's still good arguments for why we should be supplementing our ozone layer with things like sunscreen. We talked about the different ranges of UV light, UVA, UVB, UVC. How UVA kind of goes straight through the ozone layer. UVB is like mostly blocked, and UVC is entirely blocked by the atmosphere. So it's the UVB that's the worst for us, that we're protected from by the ozone layer. So you can imagine people's concern when people monitoring the health of the ozone layer noticed, starting towards the mid to late 1970s, a drop in the amount of ozone that was present in our ozone layer. And what this is showing, this graph, is going back to 1926, ozone levels measured over Switzerland at different times of the year, and you can see it sort of, it goes up and down and up and down. It's seasonal. It depends on lots of different factors. But you can see more or less the level was pretty steady for a good 50 years. And then you can see it starts to drop. So how do they measure these levels? What they actually do is, because they know ozone absorbs certain wavelengths of light from the sun, they just measure on Earth the amount of sunlight coming down, and they look at ratios between different wavelengths. And they know, depending on that ratio, how much of certain wavelengths must have been absorbed by the ozone layer, and therefore how much ozone there must have been in that direct line from where the measurement was taken to the sun. So they can see kind of the path that that light must have taken and therefore figure out how much ozone there was in the way. And you can see it kind of goes up and down and up and down and up and down, and you know, it's pretty noisy, I guess I would say. You can see starting in 1980, it changes to that green line, and that's when they changed the way they measure it from ground-based to satellite-based. So satellite can basically detect the amount of UV coming directly from the sun with no atmosphere in the way, and then you can take another measurement on Earth and subtract the two, and then you get a kind of a more accurate measurement of how much ozone there is up there. And you can see there's this drop. It's about roughly a 3% per decade drop that started in the late 1970s and continued to the year 2000. Okay, so this had people quite concerned, and for obvious reasons, right? Like if the ozone layer dies, disappears, we get all this UV flooding the surface, and that's going to cause, first of all, us direct harm, but also that UV light is harmful to a lot of other things too, like organisms in the environment that evolved in the presence of an ozone layer, materials we leave outside, like our siding on our houses or car paint or anything like that. So people were obviously concerned when they started to notice this drop, this decay of our ozone layer. But nobody knew why initially. Nobody knew what was happening to the ozone layer, why it suddenly started to disappear. And remember when I said when there are large-scale problems with the environment, there's 3 steps that are necessary to fix the problem, where the first step is identifying the cause of the problem. Second one is finding a solution, finding a technological solution to the problem. And then the third one is politicians that force through regulations or through law or through international agreements, force people to adopt those new technologies, even if it costs the industry a little extra money. We saw that sort of stepwise process already play out with our acid rain issue. So at this stage in 1970, we're at that first stage, trying to figure out what's even going on. Why is this ozone layer disappearing? A scientist, a chemist named Paul Crutzen, discovered that nitrogen oxides, remember nitrogen oxides? These are the ones that are generated from engines. If you burn oxygen and nitrogen, high temperatures and pressures, that nitrogen oxides can destroy atmospheric ozone catalytically. What catalytically means is that, you know, these nitrogen oxides can start off chain reactions where one nitrogen oxide molecule may be able to take out dozens of ozone molecules. Okay? So this was fine, except for one problem. This didn't really explain it because the nitrogen oxides that we emit on the surface of the planet don't actually make it up to the stratosphere. They kind of rise up, they get up so high, they generally fall back down to the earth with rain, with precipitation, they get scrubbed out of the air naturally. And so almost none of it makes it to the stratosphere. So it doesn't explain how nitrogen oxides at the surface of the earth could impact stratospheric levels of ozone. It was pointed out, though, that we do put a little bit of nitrogen oxide gases up there. For example, this plane that you see here, does anyone recognize that kind of plane? It's kind of a classic type. It's called the Concorde. And the Concorde jets, I think there are none that are still flying. I think one, I don't know how long ago, 15 years or something, 10 years, the last one crashed into like some suburbs in France somewhere. I forget the details. Anyway, these are planes that were like really, really fast. They fly in the stratosphere and they put their exhaust directly into the ozone layer. So there was a fear that, you know, maybe these planes could be doing something, but overall it didn't really explain the issue. 1974, 4 years later, 2 other chemists, Mario Molina and Sherwood Rowland, show that there's another substance that we produce that actually can do the same thing. And those substances are compounds called CFCs. CFC stands for chlorofluorocarbon, and they're often given the common name freons. So you may have heard of freon before. Freon is just a gas. It's got all kinds of different uses. This is an example of a freon or a CFC. They contain chlorine, 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 chlorine. They contain fluorine, and they contain a carbon in the center. So that's where the CFC comes from, carbon, fluorine, chlorine. And these gases, these CFCs, when they were first developed, people thought they were amazing because the gases are like completely non-toxic, so you can breathe them in all day. They can be present in our, they're very stable. They don't have a smell. They don't catch on fire, which was important. So that, you know, using these gases don't impose like an explosion or fire risk. So they were kind of like fantastic for the uses that they were used for. Remember our unit a few units ago talking about bonding and covalent bonds? In these CFCs, there's covalent bonds bonding together these atoms, where each of these lines is an electron pair. And those pairs are shared between those two atoms. And based on the position on the periodic table, you can tell how many bonds different elements like to make. Fluorines and chlorines are in the same column of the periodic table, and they like to make just one bond. Carbon likes to make 4. So these molecules have a really stable arrangement of elements, of atoms. All right, so here's two CFCs. This one's called Freon 11 or CFC 11, Freon 12, CFC 12. You know, there's a whole variety of these. There's dozens of them with just slightly different structures, but the same elements. So these freons are kind of like a post-World War II invention. World War II, you know, it finished in 1945. And shortly after, freons were invented, and it was discovered we could make them really cheaply, and they were used in all kinds of different applications. In fact, one of the applications they were used in, the most important one by 1974, was as propellants. So what's a propellant, you might say? Well, if you buy a can, like you know, like a spray can, you go psh, for, I don't know, hairspray or cooking spray or anything that you, like spray paint, anytime you have those spray cans, what's in there is whatever the liquid is that you're trying to spray out, like the paint or the hairspray, plus there's a pressurized gas in there as well, so that if you pump it, if you open it, the pressurized gas wants to rush out and bring some of that spray liquid with it. That's how those cans work. Well, these CFCs they thought were fantastic for use inside these cans because they didn't react with anything. They were stable for years and years and years. And they didn't catch on fire, so these canisters, having them around, wouldn't explode if there was a fire or something like that. They were non-toxic, so you could spray them all around your face in the case of hairspray. And you know, they had all of the qualities that people wanted these propellants to have. So they were used extremely widely. Refrigerants was probably the secondary use. So a refrigerant means when you have a refrigerator or an air conditioner, the way these work is they basically take a gas and they compress it, and when they compress the gas, heat is released, and then they take that compressed gas and then expand it in a different area. And when it expands, it gets cold. And they take it and put it back to the first area, compress it again, and expand it. Compress it and expand it. So in a fridge, the way it works is the expansion part takes place inside the fridge, and the compression part takes place outside the fridge. So you go outside the fridge, compress it, all that heat goes into the air, and then you bring it into the fridge and expand it, and it draws heat out from the inside of the fridge. The exact same thing works for air conditioners, similar for heat pumps as well. So they saw these gases as the ideal gas to use inside air conditioners and fridges, because if there was a leak, then it didn't like poison everyone in the room. If there was like a spark, it didn't blow up. And these gases, you could put them in a fridge and they'd last decades and decades and decades and not decompose or break down or need to be replaced or anything like that. So, I mean, they were fantastic molecules for what they were. Cleaning agents actually was for dry cleaning. Dry cleaning uses a compound called PERC now, which is called perchloroethylene. So they were using these freons at the time in dry cleaning applications. Blowing agents are kind of like propellants, but more for if you are spraying not like a liquid, but you're spraying like a foam. So if you have like blow-in insulation and you like spray it almost, and do you ever see those cans you get of insulation and it sprays out this foam, then it just kind of grows and fills the space? You know what I mean? There's a gas in there that's expanding, and that gas for many years was this stuff as well. Cool, so you can see kind of how the use here has skyrocketed going up to 1970, and that's thousands of metric tons. So, you know, we're hitting like 300,000 tons of this stuff being produced each year. So lots of it definitely put into use. Most of it, like all of the propellants, end up just floating up into the air. So what Molina and Sherwood showed in 1974, which is this point in the production graph, was that the CFCs can actually find their way up into the stratosphere. They don't come down with the rain. They're not very reactive. They just survive in the atmosphere. The same thing that made them useful in the applications made them a nuisance when they got up into the atmosphere, because they just kind of hang around and do nothing until they found their way into the stratosphere. And it turns out CFCs can absorb UV light as well. And when they absorbed UV light, this chemical reaction took place where the CFC would absorb the light and it would just spit out an atom. It was like a covalent bond would just break. UV light is strong enough to break bonds, and you have the rest of the molecule, CFCl2, and then you have this chlorine atom. And sometimes we call these chlorine radicals. And they're radicals because they have an unpaired electron, which, you know, if you've done some chemistry courses, you might know that compounds with unpaired electrons are actually very reactive. So then this chlorine is flying around the stratosphere, and it's going to react probably with the first thing that it bumps into. And if it's in the ozone layer, it can react with a molecule of ozone. That reaction looks like this, where you make an O2 and ClO. ClO can react with other oxygen atoms, and it can reproduce Cl2 and make a second molecule of O2. I think that will actually react with O3. So in this series, it's actually killing two ozones in this two-step process and regenerating that chlorine radical that started things off. So we say, this is what we say is a catalytic reaction, where this reaction can have, this chlorine can turn this reaction on again and again and again and again. Every time this cycle happens, you lose two ozones, and the chlorine keeps coming back and coming back. And so the chlorine can, like, you know, it's not like one chlorine takes out one ozone. One chlorine can take out thousands of ozones. In fact, they estimate, on average in the atmosphere, each chlorine atom takes out over its lifetime about 10,000 molecules of ozone. So you don't really need to put a lot of CFCs up there before you get this particular issue. There are other processes, other reactions I'm not showing here that can remove it from the atmosphere. So it doesn't like live forever, but it can live a long time and can do a lot of damage during that time. So people understood this. This is published in Nature. Remember, right back from the beginning of the course, I said Science and Nature were like the top two journals. This was published in Nature, and this was reprinted in 1974. Stratospheric sink for chlorofluoromethanes, chlorine atom catalyzed destruction of ozone. So step one is complete. Two chemists figured out why the ozone layer was disappearing. So what did people do about it? Well, they put a warning on spray cans. The warning said this: contains a chlorofluorocarbon that may harm the public health and environment by reducing ozone in the upper atmosphere. So, you know, certainly far, I would say, from a strong reaction. It's not like they banned it or suggested we put in regulations to limit it in any way. It was just like, well, we'll tell people it's probably not very good. And they kind of left it there. And you can see it can affect deodorants, cologne, hairspray, perfumes, all these sorts of things. Here's a magazine from the time. What's being done about killer aerosol cans? Nothing. So we were a long way yet from step 3, which was the political action to act. And maybe one of the reasons here is there was not yet a step 2, right? There was no solution except for, well, let's throw away all our fridges. Or, you know, let's not use cans anymore, or whatever. Like, there wasn't a replacement. There wasn't a substitution developed yet. So they didn't want to just ban them outright. Just like today, we can't really just outright ban gasoline because then we can't heat our homes or drive our cars or anything, right? You need to have that technological solution in place before you can really make that switch. Another article at the time: UFO aliens found at the South Pole. ETs are burning up our ozone. So, you know, along with, like you see today, credible science coming out and kind of giving the picture of what's going on. There's some more crazy theories about, you know, I guess you'd call this fake news, about what's explaining the actual situation. Now, I don't think this was serious. I don't think this is a serious publication. You know, if you look at some of these other things, this headline says, hooker gives birth to triplets, 1 black, 1 white, 1 Chinese. So yeah. This was 1986. Rub pineapple on your face to what? What does rub pineapple on your face do? Now it's got me curious. Someone Google it. If you're online, put it in the chat. Tell me what rubbing pineapple on your face is supposed to be good for. All right, so by the late 70s, US, Canada, a couple of other countries had some meetings about this ozone problem. First of all, realized it was a global problem because the ozone layer, you know, the stratosphere is high up. It's very widely distributed around the world. It's not like you pollute here and you feel only the effects here. It's felt very broadly. So a couple of countries got together to try to reduce CFC use by limiting their use in spray cans. So that was cool. If you look at the usage in 1986, propellant's slice of the pie went down to only 28%. Still being used, but like, you know, less overall. Still used in refrigerants, cleaning agents, blowing agents, and then a few other niche applications there as well. Yes? Oh, okay. So for those of you online who are dying in wait, the reason why you may want to rub pineapple on your face is because it contains an enzyme called bromelain, which I did know about, which can help apparently remove dead skin cells from your face. Okay, someone else put it in the chat just now too. It does actually have that enzyme. Sometimes if you eat a lot of pineapple, you can kind of feel almost like irritation in your mouth. Bromelain is actually a natural, it breaks down proteins, so people often use it as a meat tenderizer. So, I don't know why you'd want to do that to your face. Yeah?
It also said to like avoid pimples or like sensitive areas of your skin, but I feel like your skin is too sensitive anyway, so I don't know.
Yeah. Okay. So yeah, if anyone wants to try the pineapple thing, yeah, it says avoid if you have like cuts or pimples or anything like that. Probably not good. Someone should do their like assignment 2 on pineapples on your face. Any takers? Look, you just have to listen and you get ideas for free. Okay, so the pattern of use has changed, but the actual usage didn't actually decrease. The total usage in the 80s was still higher for CFCs than in the 70s, despite knowing the problems with it. Just like right now, our usage of fossil fuels is higher than it was 20 years ago, even though we know that fossil fuels are really driving climate change. Things took a turn, though, in 1985. I was 7 years old. What happened is people were monitoring ozone very carefully at different places all over the world, and they were noticing this slow drop, a couple percent a decade type thing. When all of a sudden, if you looked in the Antarctic, down at the South Pole, it was telling a different story. The levels here were around 200, and it dropped down to like this level, which was 100. It dropped by half. It wasn't dropping the slow little percentage like it was everywhere else. It just plummeted all at once, you know, in a very short span of time. And it created what people have now dubbed the ozone hole, or hole in the ozone layer at the South Pole. So it doesn't look like an actual hole, like you can't actually see it, right? This isn't it. But you can actually see, you can't actually see ozone with your eyes, so you can't actually detect it. You need to use equipment like what they're using here, either satellite data or ground-based data as well. This is a combination, by the way. These are like satellites, these TOMs. Another satellite, another satellite. So yeah, we have lots of satellites going around the Earth right now, some of them dedicated to keeping an eye on our ozone layer. So this is how these are sometimes drawn. This ozone hole has been mapped every year going back to the 1970s. And what they do is they kind of take a picture of the globe. You can see this point right there is the South Pole over Antarctica. And they color the different regions of the Earth based on the concentration of ozone in the ozone layer above that point. And what you can see here, the highest levels of ozone are these kind of dark red ones, and the blue, purple, black, and is the lowest levels. So you see in 1979, it actually looks kind of okay. 1980, it's looking a little pale, maybe. But by 1983, 84, 85, you see there's this well-defined spot here where the ozone concentrations at their minimum during the year are actually very low. About 100, where the peak there is like 500. So you're seeing very, very low levels at certain times of the year at the South Pole. So this is the hole, this ozone hole that you may have heard of people talking about. And you see from 85 onwards, it's just sort of grown. 86, maybe a little smaller. 87, bigger. 88, smaller. Still there in 1994. Okay? So this idea of an ozone layer hole, it's not like it disappeared entirely. It just was very low in that region that time of year. And people were watching this ozone layer every year get a little bigger. And this really captured people's imaginations, because what people realized is, well, if this continues to grow, what's stopping it from enveloping the entire planet? And, you know, we have no ozone layer here now. And people realized, obviously, that would be, you know, a bit of a doomsday scenario. It'd be a catastrophe globally. So this is a picture of the ozone hole, September 24th, 2006. And you can see the extent of the hole right there. There's the bottom south tip of South America. You can see right there is New Zealand. The reason I picked this date, this is a significant date in history. This is the day where the ozone layer hole was at its largest extent. It was never this large before, and it has not been this large since. Okay? So that you can think of as the max. So it maxed out in 2006. So here's the question. What compounds were found to be primarily responsible for the depletion of the ozone layer The answer is CFCs here. So hopefully it's pretty straightforward. Now notice, remember the skin cancer graph we looked at last class, and people had asked some questions. One of them was, why is it so high in New Zealand and Australia? And I think actually somebody brought up the fact that, what about the ozone layer in those regions of the Earth? Well, it turns out, right there is New Zealand, that is awfully close to the hole in the ozone layer. And probably, depending on the day or whatever, there may be very low levels of ozone protecting that part of the Earth. So it's highly likely, actually, that this ozone hole has contributed to the very high cancer rates you see in places like New Zealand. All right, now, I'm going to come back to this in a second. No, I'm not. So one thing that's interesting about the ozone layer hole is it only happens at the South Pole. It does not happen at the North Pole. So I'll say this about the ozone hole. First of all, it is seasonal, meaning every year it forms and then every year it fills back in. Do you remember how ozone forms? We looked at it last class. It forms because sunlight interacts with oxygen in the atmosphere. There's all kinds of oxygen up there. And every day, more ozone is being generated by the sun, and then that ozone disappears. I'm getting a phone call. Sorry, John Marimbo, I'm going to have to say no. So every day, it forms, and then it can decay. So what happens in the South Pole is because it's at the pole, it goes a lot of the year with no sunlight at all. So during our summer, which would be their winter, they go basically 24 hours with no sunlight for several months. And so during that time, new ozone is not being created. All that's happening is the ozone that was made during their summer slowly starts to decay. So it's at a minimum, and notice I said the minimum here was in September. That's when it's just finished their winter, their dark period. So there's almost no sunlight there to regenerate the ozone layer. In September, after September into October, November, December, they start to get longer, more sunlight in the South Pole, and then that ozone layer regenerates and grows back, only for the next winter for it to disappear again. The same thing should happen at the North Pole, because the North Pole gets the same amount of light. They have the same 24-hour darkness issue that the South Pole has, but the North Pole never developed an ozone hole. And the reason they figure is because the average temperature at the South Pole is colder in the stratosphere than it is in the North Pole, which causes something in the Antarctic called polar stratospheric clouds. So basically what these are just like clouds, but they're up in the stratosphere, and they don't develop in the Arctic very often. And these clouds are like, what they do is they provide a surface for these ozone-killing reactions to happen very, very rapidly. So the ozone dies a lot faster at the South Pole because of these polar stratospheric clouds, which don't really exist in the North Pole. So this is a picture which is showing the average temperatures in the Arctic, which is this red line up here, and the Antarctic, which is the blue line down here. That horizontal black line is the temperature you need to go below to make these polar stratospheric clouds. And so you can see between here and here, Antarctic is below those temperatures the whole time, so it makes them very easily, and so it's a perfect environment to destroy ozone. The Arctic, much less of an issue. So, yes, question? So yeah, the question that I got was, if CFCs are absorbing UV light, can't they provide the same protective effect that ozone can? And the answer is probably, if you had a lot of it up there, right? The problem is the amount that's up there, it might sound like a lot, but compared to the amount of ozone, it's not even close. And it's the fact that one chlorine can take out 10,000 ozones that manage to give it that negative effect. So I wonder if we didn't have an ozone layer and we wanted to generate one, if you just took a whole lot of it up there, could you do that? Maybe, maybe. You'd need like thousands of times more than we produced at our peak to do it. And there's excellent reasons why we would not want to do that, as we'll see in the future. It turns out these CFCs are also like the most potent greenhouse gases we've ever known. And we'll look at that in more detail in the next unit. So they have other problems too, in addition just to destroying the ozone layer. So people wanted to get rid of them. Makes sense, right? So we started this, we had this international agreement. We called it the Montreal Protocol. It basically was heads of state from many different countries met in Montreal in 1987, and there's 43 different countries represented. They agreed to restrict the amount of CFCs they produced back to 1986 levels. Okay, so they said, okay, they were still using a lot in 1986, but they said, let's not make more than we were making last year. Okay, so we're going to stop increasing the amounts. And work on bringing it down to half by 1999. What's interesting is previous attempts by different groups or different individuals or different individual governments to reduce CFC use was met with really harsh opposition by the chemical industry. Chemical industry was making bank selling these CFCs, right? They didn't want to stop selling them. So they opposed, through lobbying efforts and things like that, any political attempts to try to limit their use. But by now, 1986, they had changed their minds. Chemical industry was on board with getting rid of these pesky CFCs. So why is this? Well, according to the former head of the UN Environment Program, the chemical industry supported the Montreal Protocol in 1987 because it set up a worldwide schedule for phasing out CFCs which were no longer protected by patents. This provided companies with an equal opportunity to market new, more profitable compounds. So up to this point, CFCs were covered by patents, which means they could charge a lot for them and make a lot of money. When a patent expires, what that means is anybody can make them, and when that happens, the value goes way down. You see this a lot in medicine, where you can have generic drugs or you can have name brand drugs. When a company develops a new drug, they're the only ones that are allowed to sell it for a period of about 10 years. They're very expensive until they become generic. Once they become generic, then the price drops by a factor of 10 usually. So what they were saying was, well, let's get rid of these ones that we can't make money off anymore so that we can put out something to replace them and have new patents on those things so we can start getting rich again. So it wasn't this sort of like altruistic, let's do what's best for the environment and hold hands and, you know, this sort of thing. They were looking to make money, of course. They met again in 1990. It turns out they were seeing very rapid success in phasing these things out. So they agreed to 100% phase out by 2000, by the year 2000. And this is the usage chart. Remember we stopped over here before? That's when they identified that they were a problem in spray cans, so they tried to limit their use. Dropped a little bit, but then kind of went back up. 1987 was like here, Montreal Protocol, and you can see how drastically they were able to drop the amount of production. So by, this is 1995 here, they're pretty well down to like 5% of where they were at their peak. However, the ozone hole is still there. Our ozone layer has not yet healed. This is, by the way, like predictions of how much chlorine there's going to be in the atmosphere into the future. This is kind of an old prediction now. This was done like around 2005. They know it peaked around the year 2000, the amount of chlorine in the atmosphere. Problem is, if you're producing CFCs, and you stop production. Well, all of the CFCs that has already been made takes a while to find its way into the atmosphere because it's in fridges and air conditioners that have yet to break down. It's in spray cans that have yet to been sprayed. It's in all kinds of different things. It's in insulation, which slowly leaches it out into the atmosphere. And it peaked in the year 2000. And since then, the chlorine levels have been slowly coming down. But there's still a lot of chlorine up in the stratosphere. Even though it's been, what, 30 years since we made any new CFCs to put up there. Not quite 30 years, maybe 25. The reason is that CFCs are super stable. Even in the stratosphere, they hang around there for many decades. So while we kind of fixed the problem from the perspective of, you know, we cut off the source, it's going to be another 100 years before it's back to like it was in, say, 1940, before we even invented CFCs. Okay, so it's good. We're on the good side of it. You know, it's getting a little better every year. But this is going to be a long-term problem that, what year is it now, 2020? Your great-grandchildren will probably read about this in history books, and they'll hopefully enjoy an atmosphere that it was like 100 years ago. Nobel Prize in '95 went to these three chemists, Crutzen, Molina, and Rowland. These were the three folks that figured out what was destroying the ozone layer, which led to development of alternatives, which led to political action and solving this problem. It's something you don't really hear about anymore. Even though the problem is still here, largely, it is getting better, and all we can do at this point is allow the atmosphere to take its time, gradually heal, and hopefully get back to normal soon. Who won a Nobel Prize for the discovery of the causes of ozone depletion? That's easy. All right. Why does the ozone hole only form at the South Pole and not the North Pole? And the reason is the last one. Polar stratospheric clouds only form at the South Pole, which causes the loss of CFCs to be accelerated. This was the ozone hole 2 years ago. So it doesn't look that much better than it did at its worst, which was 2006. It still forms every year, like clockwork. Every year, maybe it's a little bit smaller at its maximum than it was the previous year. So it's just gotta wait, this slow, slow thing. That's the ozone hole last February, though. Do you see an ozone hole there? Now that looks pretty good, doesn't it? Why? What's going on in this picture? Do we fix it? Yeah. That's right. This is February, right? That's like, so in February, it's their summer down there. All kinds of light, all kinds of ozone being produced all the time. There's no hole just because of the time of year. September is the worst time. February, yeah. There was a website, and I don't know if it's still up, but you could go every single day and get a picture of the ozone layer for that day. And then it would go up at like noon or something, and you could go click it and like, this is the ozone hole today. And you could track it day to day if you were interested. So this is what they suspect for the future. 1971 was kind of the last time there was no evidence of an ozone hole. 2017 is this. They think this is what it's going to look like in about 20 years, 2041. There'll still be kind of evidence of a hole, but it won't be as severe as it is now. And 2065, that's like another 40, 45 years, it becomes even paler. And by the time it gets back to 1971, you're probably looking at 2100, the year 2100, which is just 80 years away. Not too bad. So how do they do this? How do they replace these things? Obviously, we still have aerosol cans, we still have refrigerators, and we still have air conditioners. If anything, air conditioners have become way more prevalent. The first thing that they did was replace the CFCs with a new class of compound called HCFCs. So HCFCs are hydrochlorofluorocarbons, as you can see in the name here. And what these have are structures like the ones you see below. And these were intended to be temporary right from the beginning. They look a lot like CFCs, except one of the atoms is replaced with a hydrogen. What this hydrogen does is make these a lot more reactive in the atmosphere and makes like 95% of it never even get up into the stratosphere before it reacts with the air, reacts with oxygen, comes down in rain, and ends up in the oceans, where there is probably broken down by bacteria or whatever and gone forever. However, some of it still does get up into the stratosphere, so it's not like a perfect fix, but it helps, right? These have then been replaced by HFCs. Remember, every time they replace these things, it's like the chemical companies have patents, they can get all this money, then they get phased out for the next thing, which they have patents for again, et cetera, et cetera. HFCs, again, are similar, except they get rid of the chlorine altogether. So these ones are best because they don't have any chlorine. Even if they get up into the stratosphere, they can't do anything. They can't damage the ozone layer because they can't make those chlorine atoms, which Roland has showed was sort of the big item there. But these are strictly regulated under the Kyoto Protocol because these compounds are like way, 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 way worse than CO2 for forcing climate change, global warming. Okay, they're like something like 20,000 times worse for a liter of these things versus a liter of CO2 going into the atmosphere. So they're better in a way, but they have other issues. 610, what was the international agreement that led to the phase out of CFCs? And this was the Montreal Protocol. Might remember. Despite the passing of international agreements to phase out CFCs, why has the ozone layer not yet fully healed? The reason is this last one. CFCs have a long time in the environment, and they will remain up in the atmosphere for many decades to come. So lots of, you know, if you're interested in chemistry, there's lots of work actually for environmental chemists looking at rates and reactions of different things in the environment, modeling, predicting what the future is going to be, and of course this has all led to us identifying a really bad problem before it ended up getting out of hand. Yeah, we're kind of done this particular unit, and what's interesting is like our chemistry building just got renovated like 3 years ago, 4 years ago maybe, 2018 I think it reopened. And one thing that we had the opportunity to do when we renovated our building was to go through and get rid of a bunch of stuff that we didn't need anymore. We had this like dumpster out back, and we filled it with all sorts of things. So, you know, a lot of it was like garbage in a sense. Like in chemistry now, when we use glassware, we have something called ground glass joints, which allows you can fit two pieces of glass together and they seal into each other. And so you can construct, you know, items of glassware with these sealed joints. These are a relatively new invention, probably like 50 years ago. What they did instead was use rubber stoppers and poke holes in them and use tubing to connect. We don't use those anymore, but we had like, I don't know, like drawers and drawers and drawers and drawers full of old rubber stoppers, every size imaginable, with 2 holes, with 1 hole drilled in them, and all these different things. And nobody had used them for decades. And not only that, but they became all like hard and brittle, so they were kind of no good. So stuff like that. We got rid of all kinds of old junk. And going through the junk, we found a box that contained 6 canisters of Freon, which is really interesting to see. Like, I guess Freon at the time was just a chemical that you could buy in a pressurized jar, and I don't know why we had it. Nobody who's currently working knew anything about it, but it was probably somebody who's retired 30 years ago who had it from the 1960s or 1970s when it was still legal, and that was it. Another chemical that got banned in this process is a compound called carbon tetrachloride. It has the structure CCl4. It's technically not a CFC because it has no fluorine in it, but it does have chlorine, it does cause depletion of the ozone layer, and it was banned in the Montreal Protocol. This used to be a very common solvent for organic chemists. And I've talked to old chemists who would say like they would use it in their lab and they would use it to wash their hands before they would leave the lab and go for lunch. And they would pour it on their hands and wash their hands with it and put it in the sink, shake their hands off and go. And it was great for washing anything kind of oily or greasy that was on your skin away. But they, of course, had no idea what it was doing to the ozone layer at the time, and of course, since has been gotten rid of. I found a receipt where a 20-liter drum of CCl4 was purchased by the department. When we were cleaning up, they found some of these old receipts, and they bought this 20-liter drum of this stuff for like $8 or something. You know, and that's like $86, so that's probably more like $25 or something today or whatever. But, you know, 20 liters of this stuff, it was just used like nothing. Put it in spray bottles, wash glassware with it, whatever. Also, people didn't care about what happened to it afterwards. It's not like they collected the waste. So it turns out now, carbon tetrachloride, if you wanted to buy it, you still can. It's heavily regulated, which means heavily taxed. So if you want to get a little bottle of like 100 milliliters, you could probably get it for $500. Or like $495 of that is tax. And that's the way they regulate these things often. Is not just ban it outright, but like put so much tax on it that it's prohibitive and that you would never use it in industry in large amounts. You'd look for an alternative. But there's certain reasons in chemistry why carbon tetrachloride is the best for certain things. So we have in our department some like legacy bottles, and we treat it like gold because we realize we could never afford to replace them, probably. And there are 4-liter containers of carbon tetrachloride, and I've used it a couple times. Every time we use it, we distill it all carefully, clean it, put it back in the bottle, cap the bottle really tight. So like we make sure none of it escapes into the atmosphere. All of the reactions are done in sealed containers, so we get all of our material back. And we've been using these like same 2 4-liter bottles as long as I've been here, 15 years, and with no losses. So yeah, we've become extremely careful with this stuff. So yeah, pretty interesting and pretty useful as well. Okay, so what I'm going to do now is we're going to move to our next unit, and our next unit is kind of related in that our next unit is going to be kind of our third and final unit that's going to be on air pollution. And I guess the common factor in everything we've been looking at so far has been that we are dealing with gases. All the air pollution. Obviously, if it's in air, it's evaporated, it's a gas. I suppose with the exception of the particulate matter, which are solid particles that are suspended in the air. The third one is going to be looking at global warming and the other polluting gases. This is, I think, a more contemporary environmental issue, of course. The other ones were big problems, got solved. I'm hoping by the time I can retire this unit, I can teach the exact same thing. Problem, we had, identified it, political action took place, and we solved it. So global warming, it's been interesting to me to see the public discourse around global warming / climate change as well, because different people at different periods of time has had sort of different levels of denial. And I look back to like the early 90s, where it seemed like an urgent issue at the time for me, where people were arguing over, is it even a real thing? Do we have evidence for this? Is this even true? So I'm going to show you some of the evidence that suggests that definitely our climate is changing. This is a picture of the Moyer Glacier in Alaska, 1941 versus 2004. And this is taken from the same vantage point, and you can see essentially this glacier has retreated all the way up to there. This is another one in Norway, 1928 versus 2002. You can see this, it's all melted away. This is one in Argentina, Sala Glacier, 1928 and 2004. It's particularly an issue in the Andes Mountains in South America because these glaciers, as they melt, create rivers and streams, which are the main sources of drinking water for much of the population there. So if these evaporate away or, melt away, there's likely going to be freshwater shortages. Here's one in Canada. This is the Athabasca Glacier. And what they've done starting in 1992 is they put these like rock markers each year at the edge of the glacier. You can see the glacier where it's retreated to here. And my guess is that the space between these stones is only growing each year. I actually visited a glacier 2 summers ago in Iceland. And kind of the center of Iceland is sort of one big glacier. And when you go to the edge of it, it's actually like very surreal because I went on this expedition, which basically the melt water from the glaciers melts all these caves into the glacier along the edge. And you can do like hikes inside the glacier through all of these like tunnels. And you need these like special shoes with really like hardcore crampons, and you need, the helmet and all the gear and everything to go in there. But we did, and it was nuts. It was like you're walking in these caves, and there's like a full-on torrential river running by. And that river is meltwater, just from that glacier. And the guides were like, you had to get in this like all-terrain vehicle and like drive for like half an hour to get to the edge to begin with. And they say like, every day it's like an extra 200 meters they got to drive because it just keeps retreating and retreating and retreating before you can get in there. So it's like melting that's in the summer. It's the fastest melting period as well in Iceland. And, but definitely you can see glaciers all over the world shrinking and disappearing as a result of this. Now there's a huge amount of water tied up in these glaciers around the world and in the ice caps. Another thing is you can just measure the temperature at the surface of the Earth. This is a bit of a complicated measurement though, because how do you come up with one temperature for the entire surface of the planet, right? How do you average these numbers together? So people have ways of doing this, and I don't fully understand all the math, how they arrive at these numbers, but this is basically what they call temperature anomalies. So what they do is they go from 1951 to 1980, which is like this period, and they take the average in that region as being this horizontal line right here. And then every other year outside of that range, they plot the average temperature for that year as either warmer than that average or colder than that average. And so you can see definitely since 1980, that anomaly has always been positive every single year up to about 1 degree Celsius. So I guess you could say is compared to say 1970 on average, our Earth right now is about 1 degree Celsius warmer than it was then. And it had been rising before then too. You can see almost like from 1880 to 1920 or so, the average there is, not a full degree colder, but a little bit colder for sure. So this is causing all sorts of different changes. Actually, you can see these changes in the Annapolis Valley quite a bit. If you drive really any distance through the Annapolis Valley, what you'll see everywhere are vineyards where people are growing grapes. It's only been kind of recently that we're able to grow grapes here really at all. When I moved here in 2005, there was one winery in the whole valley. And it was the Grand Prairie Winery. And now there's, I don't know, at least 20 probably. There was another one in Nova Scotia. There was 2 in the province. The other one was Yost, which is a much older one, I think. There's 2 things that happened. One, climate change actually extended our growing season long enough that it became economically viable to grow grapes here. The second change as well was advances in like cultivation of grape plants to produce varieties of grapes that would thrive in our environment. So those 2 kind of like were coming at this problem from opposite directions and made it so that we can now grow certain types of grapes. There's lots of types of wine grapes that we can't grow effectively here yet. And so, you know, it's not like we're going to replace California or some of these other wine growing regions. This is a picture of the planet showing between the years 2014, 2018, the temperature anomaly, and this is in degrees Fahrenheit, compared to that 1970 value or the 1950 to 1980 average. And what you can maybe tell from this graph is that this surface warming that we've identified has not been uniform. Some places warmed up more than others. You can see kind of over here, there's this whole region that actually got colder. Most of the warming, the reddest areas, I guess you could say that, have been in the north. So the north has warmed up a lot more than like equatorial regions actually haven't really seen too big of a difference. It warmed up maybe a little bit, but not really a whole lot. By the way, the reason they think it's cold in that area is because of melting ice causing a strengthening of the Arctic current. So that's bringing more cold water and more cold weather down from Arctic areas. So like Newfoundland hasn't gotten any better, any warmer. Sorry, folks in Newfoundland, but you're kind of close to that area right there. So there's every year, people check out the polar ice caps. They basically, you know, the North Pole is covered in ice during the winter, and it recedes during the summer every year, and then it expands back again every winter, kind of goes back and forth and back and forth. And they monitor the extent of sea ice cover each year, and they draw these graphs. So in 2012, this is a picture. You can see the white is where the ice is covered. This outline here, and when I say that's the area the ice was covering, this was the minimum for that year. So when the ice was at its absolute lowest, which is probably towards the end of the summer, this is what its level was. The average minimum for like the previous decade is that orange line. Just to show you how in 2012, how much smaller the ice coverage was in the north compared to what the average had been just like a decade earlier. There's all kinds of ways of showing this information and showing this data. This is one way that they do it. This gray line here is showing the rise and fall with the sea ice coverage in terms of area. You can see it's in millions of kilometers squared. So by September, it's at a minimum. It's a maximum by the end of the winter, this time of year, March. And it kind of just goes up and down and up and down. And this gray area, the line is the average between 1981 and 2000. And the hazy gray area around it, the thick line, is kind of the range that it's fallen in during that time. It's technically plus or minus 2 standard deviations of that number. And then, so you can see, you know, in years since, 2012 was a pretty bad year. 2019 is this black year, right? And it's every year just a little bit lower, a little bit lower, a little bit lower. Sometimes it goes up a little bit, and sometimes it goes back down a little bit. So it changes maybe a little bit year to year, but there's been a long-term trend. And this particularly, the sea ice problem, has been really hard on certain species, like polar bears, for example. And this is a graph showing basically the minimum sea ice extent. starting in 1979 and going to, I guess that's 2000, probably like 17, 18 maybe. And you can see that blue line is the trend line. It's clearly long-term decreasing. But in any given year, there's a bit of noise around that line. It could be up or down. It's not super sticking to that line. And so what happens is you'll get a year like 2005, where it'll be like really low, and people will be like, man, we've got an issue. And then the next year, it'll be up here, and everyone will be like, oh my God, somehow it fixed itself. It's now increasing. We're doing great. But that's looking at a very short-term trend. Like imagine this year. People were like, oh, okay, the ice is fine. It's not shrinking anymore. We just had 2 years of increases, and then you get this big dip the next year, right? And it's just noisy data. It's just going to go up and down with this long-term drop. So that's another thing with this data is it's important to always look at long-term trends and not just stick to short-term trends, because the short-term trends are not going to be showing the entire picture. We have a new island, Antarctic. I'm probably not saying that correctly. This is a new island that belongs to the territory of Greenland. Greenland, I believe, is territory of Denmark. And this was an island that had previously been covered completely in ice 100% of the time, year-round. And because of global warming, because of this decrease in sea ice extent, it's been exposed now. So they have a new island territory, I guess. So that's the name of it. That translates into English as warming island. So they recognize, of course, that this island exists now because of warming to the area. Did you know there's a little island that's disputed territory between Greenland and Canada? It's like a small little island, and Canada claims it as part of Canada, and Greenland claims it as part of Greenland. And so what happens is there's like the Canadian Navy, I think, kind of like guards it, and so does the Danish Navy. And what happens is like Canadian sailors will like once a year visit this island, and they go look for the Danish flag, and they pull the flag out and plant a Canadian flag, and then they leave a bottle of Canadian whiskey. And then when the Danish come a few months later, they pull out the Canadian flag and put the Dutch flag back in and leave a bottle of like something else, I don't know, brandy or whatever it is. And that's just sort of like an ongoing, like good-natured kind of like a, that's the kind of territory dispute you want, I guess, right? But anyway, I should look that up, what that island actually is. Thomas Martin asks, how do we know how the 2020 lockdown affected global warming? That's interesting to know. I don't know the answer to that question. I mean, I guess the idea being is that the amount of gas that people were burning went way down. International flights basically dried up. To a certain extent, manufacturing fell. All these sorts of measures, all these things that were highly polluting activities would have been putting less CO2 in the atmosphere. It'd be interesting to look at that data. I'm going to see if I can find something on that for you. Donald Trump, this is back in 2014, before he was president. This very expensive global warming bullshit has got to stop. Our planet is freezing, record low temperatures, and our global warming scientists are stuck in ice. So, you know, like, despite all the evidence that this is a real threat, there are still those who want the narrative to be that we're fine, that we don't need to worry about this, this isn't a real problem, we certainly don't need to affect the way we live or the way we produce things, right? And you can see this a lot. This isn't just Donald Trump. There's a lot of people with this attitude, and this is, or has the potential to be, a very serious threat, I guess, to any action taking place on this. But one thing I'll say is it's like I've seen the narrative change over the last 15, 20 years. I would say like if you went back to the year 2000, this was very much a very common issue. There would be like, global warming's not even real. We don't have to change what we do. I'm gonna go get a big jacked up truck, burn, you know, all kinds of gas, whatever, we don't have to worry about it. Where it's, I'd say people now, I'd say it changed from that to, okay, global warming's definitely real, but it's not humans that are causing it. It's some natural process, and the world's always been warming and cooling in cycles and so on. So it's kind of changed from it's not real to it's real, but it's not our fault. And now it seems to be moving to the territory where nobody denies really anymore that it's our fault. So progress has been slow, but there has been progress, as far as I can see. Sea levels are rising. We know this for sure. This is going back to the early 90s. This is the average sea level rise, I guess, like 2 years ago. It's raised, these are millimeters, so you know it's not super dramatic, but this is like a 10 centimeter increase in average sea levels around the planet. This is, if you go to Fortress of Louisbourg in the northern part of Nova Scotia, close to Sydney, what they have is this kind of wall where you can see the high tide level in 1743. And this is the high tide level in 1998. Notice the difference there in height, right? And there's a guy standing here to give an idea of scale, right? So that's probably like maybe a 4-foot difference. But I will say this, that sea level difference is actually the result of 2 factors. One factor is sea level rise, which we know has been the case around the world. But the other factor is actually Nova Scotia sinking down, like it's the ground actually lowering. It's a ground, I don't know what they call it, recession or something like that, where the ground actually is sinking lower and lower. And this is a natural geological process. Some places are sinking, some places are becoming more elevated. That's how mountains eventually form and so on and so on. Nova Scotia happens to be at an area that's going down. Oh, someone answered my question. It's Hans Island and the Danes leave Schnapps. So there we go. So yeah, so this isn't all sea level rise. Partially maybe is. Okay, so I have a question, and I think maybe I'll just cut her short at that point. Where have the greatest temperature increases due to global warming? Where have they been located? And the question is close to the North Pole. What is significant about Unartok Kekertak, located in Greenland? And it is a new island, in quotes, recently exposed by melting sheet ice. Okay, that's it for us for today. We only have a minute or 2 left anyway. We will continue talking about global warming, nice cheerful subject, next Thursday.